Wave functions and quantum states, chapter 4. It goes from page 56 to 67. That is 12 pages. I don't do work additional reading or preparation or whatever, so we're doing this together. I'll tell you in the video or put it in the description if there's anything else that I'm doing outside of the process. Although yesterday I did query Copilot, Microsoft Copilot, about my learning process. I think which I linked into the previous video, what we discussed, part of it. I'm just gonna have a look over this key points before I do my little notes, just to refresh my memory. Schrödinger, mathematics, properties of electrons, wave functions. Develop mathematic wave-like properties of electrons of atoms involving wave functions. So Schrödinger, wave function, wave-like properties of electrons. So this mathematical function that he developed describes the wave behavior of the electrons within atoms. So somehow the atoms somehow the electrons in atoms have wave-like behavior. They although the electrons are particles, they are sort of wave. They display wave features, and that is what Schrödinger did with his wave functions. He described that wave behavior. The probability of finding a particle in a specific quantum state. Werner Heisenberg, mathematical theory. Ignored knowledge about where a particle was before the moment of its interaction with other quantum systems. That's usually how mathematics is developed. It goes step by step. What happens to the thing from point A to point B? But he didn't go about it. I mean, the electrons make changes from the one quantum level to the other. And his mathematics didn't take that into account. What happens from A to B? He just say that's what we can say about B. Upon making an observation of the state of a particle, the full wave function of all possible states collapse into only one final state, which is called the Copenhagen interpretation. Collapse into only one final state. Oof, I'm a bit jacked up, so I've got to try and calm myself down. It's not good to be in an excited state when you're trying to study. Be as calm as possible. Try and make a video about practice I do to take control of the nervous system. Heisenberg's uncertainty principle. Fundamental limit to how well quantities such as energy and time, momentum and location can simultaneously be known with infinite precision. So uncertainty principle. These measurable quantities of of the electron. So I always talk about two quantities because it could be other quantum. There's other quantum systems than just electrons. I think photons, whatever. Momentum and location, energy and time. You can't measure these with infinite precision. Schrödinger and Heisenberg's quantum theories led to the first precise and mathematical consistent explanation for the structure of atoms, from which detailed calculations could be performed. Quantum theories, Schrödinger, Heisenberg, mathematical consistent explanation. What's happening with the atoms? Pause. I can press the recording button instead of the pause play button. But anyhow. So what are we dealing with here? Mathematical descriptions. I think they start out with assumptions and then they build the mathematics. So it's most likely that the experiments came up with certain concepts. Certain concepts came from the experiments of quantum systems. And then these mathematicians or theoretical physicists started from those and then built their mathematical theories. Wave functions, matrix algebra, uncertainty principle, Copenhagen interpretation. So there's about 3 major points. The chapter's got something about many worlds. I think I'll have to read about that. Just heard about it, but let's see. Let's start with this process. 56. This is a difficult page. Page 56. That helps if you know beforehand. You're going to have a tough time. Rutherford Bohr atom, multi-electron atoms, empirical theory, Maxwell, matter waves, atomic structure, Erwin Schrödinger, matter waves, elegant equation, how a matter wave should evolve in time and space. Matter wave, Schrödinger, matter wave. So these wave function of Erwin Schrödinger, how the matter wave should evolve in time and space. So it's that the wave function is a function of time and space. What does it look like in this point in space at that specific time? Electrons. Schrödinger successfully used his wave equation to derive energy quantum levels. However, there was a twist in the interpretation of what exactly was waving. Most physical waves can be interpreted as a change in some physical quantity such as the height of a surface. For electron waves, in order to make the mathematics work, the object that was waving was not a physical medium but a mathematical object. Amplitude squared represents the probability of an electron being in a specific place at a particular time. So this is quite a summary of what Schrödinger did. What was about Schrödinger's wave equation. How do you spell his name? Schrödinger. Wave function of space and time. That's its complex complement, I think. Probability. Space and time. I think that's what I'm going to say. It's just a mathematical wave. I said something about page 56. Let's go to 57. I'm going very slow, but this is difficult stuff. Wave equation. Analog of Maxwell's equation for electromagnetism and light, and takes the following form. That is a derivative equation. I can't remember now that operator, what it actually does, and it's squared. And there's a V. Wave equation. So you solve this equation to get the wave function, I think, and it looks somewhat similar to total energy of a particle. So there's something about energy. Coulomb electric potential of a particle of a charge E orbiting in a nucleus, distance R. This is a new way of studying for me, so I have to learn how to do this and decide how I want to do this. And I'm regressing now to reading the whole thing. My idea was to scan and extract particular system, total wave function, quantum numbers, quantum number for energy level, orbital angular momentum, particular wave function, quantum numbers. Okay, what is it? Wave equation. Schrödinger wave equation. There's something about energy. One of this is potential energy. I think that's potential energy. I'm not. Electrostatic potential energy, I think. And then state and quantum numbers. Energy levels. So what is this about? The wave equation and something about the energy levels. Let's go on. 58. Probability, space and time, probably of finding the electron. Quantum state, the function looks like for its specific quantum state. Quantum state. That's a probability of finding the electron there in that specific state. and then the wave function. And this is some history about Schrödinger. Doctorate 1914. Physics, electrical engineering, atmospheric electricity. Max Planck studied quantum models Max Planck and Albert Einstein. Geometry applied to electron orbits. Quantization as an eigenvalue problem. Mathematical technique, quantum systems. Philosophically, he never liked this perspective and once said that he had been sorry he ever had anything to do with its invention and subsequent development. What? Really? Okay. 59. Amplitude, wavelength, wave velocity and direction. Is everything going fine? Yes. 10 minutes. Ordinary waves. Something about waves. Amplitude, wavelength, speed. Imaginary number, that's a square root of -1. Complex algebra. And then we've got the wave function. Complex conjugate, product, real number. Something a squared plus b squared. Real. That's the probability. Yeah. Probability. Probability of finding an electron at a particular place. Where are we time wise? 12, 59, 60. Angular momentum. Projection of its angular momentum along the L. Angular momentum. Okay. I think maths, I can't remember. I think L might be the symbol for angular momentum. Angular momentum, z-axis, quantum number. They use a magnetic field to orientate the angular momentum of the electron. Magnetic field. And then somehow they measured it probably. Cartesian coordinates or spherical coordinates. Spherical similar to the function can actually be split in of two functions called a spherical Legendre polynomial and Rayleigh-Hermite polynomial. So it's some vicious maths. Polynomials. Electron probability grounds. Some angular momentum, some Formula. What's this formula thing? So the correct way to describe statement was through a function. The user, I think that's the lower script. What the difference is between that and the wave function. Electron probability clouds. It's L and quantum numbers. So it seems these quantum numbers might be associated with the angular momentum. Where are we time-wise? 14. I think the other one was 561. Schrödinger's wave equation, wave function, compute the probability function, probability function. Ooh. I'm gonna swap that Ln in x and t, probability function. That's from the wave function. You can get it with the conjugate von Neumann, the mathematical foundations of quantum mechanics, 1932. John von Neumann. John von Neumann. 1932. He wrote some book about all these maths, it seems. Each of these individual quantum states is collected together into what is called a Hilbert space, for which each point is one possibility for the state of the system defined. Heisenberg's uncertainty principle. Wave functions, measurable features, mathematical. Where am I time? 16. Came into moment of observation. Set of probability waves. Probability waves. I'm getting cramped, yeah. Many observable outcomes of observation, relation, non-commutation, matrix, algebra, position and momentum, Heisenberg's matrix, quantum condition, what on earth, spectral line, calculations were generally considered tedious and hard. So few physicists were willing to follow his laborious discussions fully. Crucial insight how quantum systems are measured. If you sit in these lectures, you are totally lost. Okay, so what I'm gonna do with this Heisenberg uncertainty principle. Measurements is not fine. Physical object. Non-commuting. It's about its. I think it's about its matrix algebra. A scheme for calculating the spectral line frequencies. That's page 61. Okay, let's stop it here. Let's do page 62. Werner Heisenberg and his matrix calculations. Some personal information about Werner Heisenberg, Max Born, Arnold Sommerfeld, mathematician Hilbert, with Niels Bohr, Copenhagen, University of Copenhagen, mathematical description of scattering of light by atoms, matrix approach to calculating how atoms and light interact, how atoms interact with light. Atoms, matrix algebra, mathematical difficulty, matrix mathematics, describe physical systems, Nobel Prize 1932. For the prize by Albert Einstein nominated. So he approached the maths, approached it from completely different maths. Everyone was more into the calculus sort of approach and the wave functions, but he did it completely different. Possible outcomes, collection of possible outcomes and by enormous collection of elements in Heisenberg matrices. State of a system, enormous collection of elements. So it's not meaningful to talk about what an actor is doing between measurements. Person traveling from one lamppost to another. Can't see what the person is doing in the dark. For the electron, this almost literally means in the Heisenberg interpretation that electrons do not really exist between measurements. Electrons do not exist between measurements. Exist, do I have to exist? There's no there's no C in exist. Exist between measurements. 62. I'm just trying to summarize each page without thinking about it. Which is not good, but okay. We'll save that for another time. Trying to get through the chapter. Observational measurement. What the electron is doing when it arrives at the lamppost. Schrödinger quantum theory. You see, it's two completely different viewpoints because Schrödinger's thing is continuous, wave function. And now his mathematics suggests something completely different, that in between, there's no in between from A to B, it's just at the various quantum states. We don't know what it's doing in between according to his mathematics, it seems. Total wave function, possibility sudden collapse into one state with a specific measurable quantum numbers. Copenhagen interpretation. Copenhagen. I think it was all these physicists came together at some meeting and they come to this conclusion. Collapse into the quantum state. The issue of whether the wave function of a particle actually collapses. The issue of whether the wave function of a particle actually collapses or not has been challenged by such ideas as many-world interpretation. So that's another way of looking at it. Said no, there is actually something happening in between these quantum states. It goes into another dimension or world, and then it emerges at that specific quantum state. So that's a challenge to that way of thinking. '64. Where am I time-wise? 6 minutes it seems. I've got a few more pages to do. So about 4 more pages, I think. Everett. What is going on here? I missed something here. Quantum. What happened here? 63. Many worlds. Oh, the many world interpretation. U. Everett. That's what I missed. It's his. U. Everett. Everett. GT. That's what he proposed. Archibald Wheeler. Scorn. He left first after St. Betty. So people didn't like his story, I think. According to the many-world imitation, the wave function of a system, no matter how complex, never collapses for observers within our universe. Instead, with each quantum measurement observation, the new universe splits off from the previous universe. The process of splitting allows the wave function across all spawned universes to remain uncollapsed. Is U. Everett wave function manual split at the measurement. It splits quantum state. Heisenberg motivate momentum and position of an element can be represented as complementary components. Are they going into a different topic now? Complementary components, momentum and position. I think math is called Fourier now. I think they're going into something else at this stage. Let's just see. I get the impression Yeah, here it splits. It's going into some other discussion which is not relevant to this manual. Let's see if I can construct this. Of course, here's the manual to make a measurement, and it splits, and then probably one of these emerges upon the next measurement or something like that. Multiple copies measured, spin up, spin down, 3 successive measurements. Measurement 1, measurement 2, measurement 3, and then at measurement 3 you get one of these, something like that. These people are still not probably fond of this way of thinking about it. Okay, what can I make of that? Momentum and position. Momentum and position. Heisenberg. Momentum and position. Something about components. Oh, that's components. It's the uncertainty principle that's coming out here, I think. Where are my time wise? 11. Oh, I'm taking very long. Fourier mask, position and momentum, Fourier pairs. So it's another type of maths. Complementary pair can be known with equal precision. Position and momentum. Position and momentum. Position and momentum. Pairs. Maths, Fourier maths. I think it's the uncertainty principle that's coming out here. So, waves. Fourier is something about waves, yeah. Electrical signal. Impulse. Time. Frequency domain. Wave train. Localized particle. Momentum description. Localized particle in space. Knowledge about exact momentum and speeds. Frequency domain. So I looked at this momentum and position of the system using this mathematics. The reciprocal behavior between momentum and position, and also between energy time, is the core of Heisenberg's uncertainty principle. Heisenberg's uncertainty principle. Stated as a pair of equations. That's the uncertainty in the position, momentum, and energy and time. 65, 66. Where are my time ones? At the atomic scale, if you know the location, so of an electron to within 1 nanometer, then you can know the speed of this particle better than this. So speed, that's because of the momentum. Uncertainties in energy will be discussed. Virtually all against to a self-consistent quantum theory. Mathematics, uncertainty relations, structure and prediction for measurement outcomes. Measurement outcomes. Mathematical relations, accuracy, atomics lead to an accurate description of the atomic structure. Measurement of how the wave functions for quantum system collapse. Okay. And we talked about 67. I'm not going to go into 67 again. So I'm going to stop at this one. Next time I can look at all my notes and see if I can summarize them and get an overview of the notes.